A very good morning to one and all here. I, Dr. Sonali Patil, welcome you for the ACM Summer School on Programming Languages, Principle and Practice. So we, the Pimpri-Chinchwad College of Engineering, Pune, are hosting this, and we take this as an opportunity to host this event. And I'm sure that the next 20 days will be of great learning for all of us, and we will have the lot of takeaways. And today, to begin with, we have the expert, Dr. Abhijat Vichare, like a very well-known person in the field of programming languages. So I welcome Dr. Abhijat Vichare for today's session.
Thank you. Nice to see you all of here today morning and interested in programming languages. Just to be clear, this is about how programming languages work rather than any specific programming languages and so on and so forth. It's an honor to be here on my side. I'm feeling very privileged that I will be, I'm talking on an ACM India Summer School platform. Let me, since this is the first session, let me just give a brief view about how this school is sort of conceived and will proceed. We will try to look at some of these issues that are there, discuss what makes a programming language, how are programming languages conceived, designed, developed, how do compilers, interpreters work. We will learn a lot of techniques that could be used and implement quite some of them. So this is a very intense school. We will be implementing lots of things, so you will have assignments coming right from day one, don't worry. At the end of the day, we are all teachers. So we don't really like to see you just sitting there. Unless and until we give assignments and make you work, we are not very happy. Okay, so from day one, you will have your assignments coming your way. And yes, one of the important aspects of ACM summer schools is to give you an idea about what is the state of the art, not industry-wise, research-wise. Research, let's be really clear, leads the industry far ahead in most of the fields that you are seeing. Today you might see machine learning, but from the research point of view, that has been old stuff. So we will, in this particular school, we will be talking about programming languages. Okay, some quick suggestions for you before I begin anything. Please make your own notes, ask questions as they occur to you, feel free to interact with the faculty. Okay, whosoever are over here speaking, they are some of the best people in the country. Okay, we have people from the industry as well as people from the academia. Okay, and yes, write code or solve problems. There is an adage in teaching: I hear, I forget. Okay, I see, I remember. I do, I understand. This last one is what is our goal. Okay, so please write code, solve problems that are given to you, whatever they are. Okay, some quick ones. This is just a note that I thought I should add up here. The host institution would have various rules for various things, residence rules, academic complex rules, and so on and so forth. Please adhere to them. Okay, help is available from the hosts at various points. Do not be shy. Please seek whatever, talk to them in case you have any problems. Okay. Use the resources responsibly, and please be careful about the video recording equipment. NPTEL, if you are aware of NPTEL, you are, right? So NPTEL has kindly agreed to record these sessions and eventually make them available online. All right. So you will have a lot of equipment, cameras and microphones and various things. The wires will be moving around. Please be careful with that. Okay. We suggest things like these. I mean, it would be good if you could form some small discussion groups. Okay. If you are not comfortable using GNU Linux, then ask around, talk to your friends who know. There are local people who are experts here. Okay. It's a matter of getting used to. Okay. Everybody knows how to use Linux? Anybody with a issue, challenge or whatever? Okay, good. The idea is to settle onto a working and stable system as soon as possible. So, we want to get working, so we do not want to get decelerated or affected by setup problems and stuff like that. All right? Fine? Okay. So, let me also give you an overview of the way this school has been conceived. What we really want to do is to show you how principles reach to practice. Okay. So, here is an example. I hope is it readable behind? Okay. The picture is to be read from bottom to up. So, the analogy that I am giving here is of some basic physics concepts that you have, like energy, momentum, entropy, torque, angular momentum and so on and so forth. There are some concepts. These are things that our minds perceive, and we sort of observe their behavior, and in our minds we sort of try to imagine what must be happening. For example, when you look at this pressure and volume and so on and so forth, if you observe the way pressure volume behavior occurs, it gives you an idea of what is called as a heat engine. Now, this is the point where ideas come out into practice, and you have various actual engines like internal combustion engine that is used in automobiles, or the jet engine that is used in aeroplanes. So, we have shown some examples there, so Bernoulli's principles and so on and so forth. Now, this is the point where you have multiple technologies that come up. That is what we are going to call as technology. Okay. Incidentally, this is a diagram fresh off the boat from one of my very recent publications, where we are trying to bring exactly these kinds of differences in the computing field. Bernoulli's principle, for example, gives you the structure of the wings and ailerons and so on and so forth. Now, multiple technologies are used to create specific artifacts. A car is where you have your heat engine and a transmission system and many other technologies coming together. Okay. This is a point, this is a design point at which each technology may have its own constraints, and matching the constraints with what is called as a typical trade-off between matching one kind of constraint and somewhat opposite kind of a constraint. How do you get them together and make the thing work? That is where your major engineering creativity goes. Or in case of an aeroplane, of course, it is your engine and the wing and lots of other things. I hope you get a sense of what is our engineering and technology idea. And once you have your artifacts done well, so the engineering of car has been successfully done, it is at that point you will be able to create a business model and deliver a service. So, taxi service, for instance. Okay. I mean, you can give taxi service only when you really have a good working car. Okay. If all the technologies have not been engineered correctly, if they do not work, nobody is really going to think of a service, a taxi service or an airline service. All right, fine. I hope this view is clear. Any questions on this? What we have done is sort of looked at the same view for computing, and in this case languages. So, you have at the bottom of the diagram, you will have some sets of concepts. How do you express programs, how do you execute them, your computability, complexity theory and algorithms. These are your conceptual mental tools. I mean, this is what you need to really have them. Your mental muscles here should be very good. At the level of technology, you have data flow analysis, lattice theory, scanners and parsers, Lex and YAC, this is stuff that you might have possibly done. Data representation, how do you represent data, control flow, function calls, and something called as abstract machines. This is a point where you take your concepts and try to realize some concrete artifacts. That's the point where I'm saying that it's technology. When you come out up to the engineering level, for instance, so when you run, for example, your GCC command, everybody has used GCC, some C compiler. Okay. You might know that given a C compiler, you can give it some optimization flags. I mean, do some basic optimization, do some very hard optimization, or whatever. Now, whatever those optimization levels are there, they actually just define a set of algorithms that are used to optimize. Choosing which algorithms at what level is an engineering issue. That is what we want to bring out. I mean, that appreciation about how really real life compilers or all these software works. You also have standards when you have languages, say for example C or C++ or whatever. The language is defined by a standard. Toolchain, file formats. The point is, standard is the one, for example, where the language in reality, its real structure is where it comes out. And you need to combine your technology, that is the various algorithms that have been conceived by various calculations. They need to be brought together to obey the standard. Making the algorithms work together is again an engineering problem, and that is where your major trade-offs are. Okay. And once you have a very well defined language with all the let me say well engineered language, when it comes up, it's at that point you have you can use that to create services to use. Services in this industry are called as APIs, application programming interfaces. So, for example, when you have the C language, you have a system API. By system, I mean the language allows you to interact with the operating system. Okay. Or you have networking APIs. There are functions defined. You just call those functions and you essentially do networking or graphics or whatever. So, this is the point where we have what are called as services. All right. This model can also be used for any other language that you know. Okay. Java, for instance. All right. So, one of the ideas of this school, the way we sort of designed, conceived this, was to show you these differences. In fact, in order to support that, the way we have sort of structured the school is more or less fairly loose, which is why the general contents are just indicative rather than descriptive. We just indicate that this is what will be covered, because each speaker has had the privilege, I would not only say privilege, the freedom to really bring out their way of talking about these things. Okay. So, at some point, some speakers may, for example, focus on concepts and technology. That can happen. Some of them would possibly focus on technology and engineering. That is possible. We also have speakers who will try to give you the engineering and services point of view. Okay. So, that is the way things have been sort of conceived. Let me sort of run you through the general weeks, I mean general material over the week. So, this first week we typically will do some basic ideas. But basic ideas does not mean that it is going to be conceptual. Basic ideas across all the 4 levels that we just saw. All right. So, for example, what is engineering in compilers would be done pretty early. Okay. Fine. Some object oriented ideas, software tools, reviews of architecture, maths, computation, some of the stuff that you have done, possibly done as courses. If not, this is just a review, you can always refer to it as and when needed. The second week will be primarily what is called as program analysis. I mean, given a program, how do you think of algorithms to analyze those programs? Okay. An exposure to that part and functional programming. Any of you, all of you are exposed to functional programming? What is functional programming? Anybody with who has no idea or has some is not confident about it? What is functional programming? So let me take a quick poll. How many of you know functional programming? Please raise your hands. Okay. So when you have, for all the people who have raised your hands, have you used Haskell as a language for functional programming? How many say yes? One. Okay. So for the others, can you give me an idea what languages have you used to learn functional programming? Gopher, Lisp. What about the others? I mean, there were many who raised their hands on functional programming. What other languages were used? Clojure and so this is the first part. This is interactive. Okay. We had a couple of moments ago, we had a slide which said, I mean, just say it out whatever you have. Unless you put it on the table, it's going to be hard to really figure out what to do. So again, what other languages have been used? Lisp. Okay. All of you Lisp? Okay. All right. So cool. I mean, functional programming in Haskell will be the primary. Haskell will be a primary language used for functional programming. It's not a very difficult stuff to do. Once you understand the ideas, which is what we will have a few sessions in the first week, this should be quite okay. We will also give you exposure to type theory. Okay. You have used types in your programming, but what really is the idea? In fact, if you look at Haskell, it is one of the coolest language in the sense that it's a strongly typed language, but we as programmers never need to specify the type. This means that you just write the program and the system, Haskell system, calculates the types and it checks, it not only infers the type, it also verifies it. Fine. So if you write a program which is type incorrect, Haskell will complain, catch you, type incorrect tha. In contrast, Lisp is typeless, just to give you a contrast of that. So some type theory will be there. Hopefully, Professor Sanyal would be able to talk about what is called as the actual algorithm of type inferencing, something called as a Hindler-Milne type system. Hindley-Milner, what am I talking about? So I am so sorry. He'll probably be doing that. This is what we have in the second week, and the third week will be primarily again program analysis. How does a compiler optimize a C program? Then something called as program semantics. If you write a program, what do you mean by what do you mean by something like a meaning of the program? How do you know that it's going to execute well? And so on and so forth. These were the questions that will be done. Evaluation strategies, again glimpses of interesting research. Okay, fine. So at all throughout the school, there will be various glimpses of what is the state of the art that is happening right now. Obviously, people who will be talking about that will be excited about it. So just make a judgment, take your own call whether you are interested, how interested are you, and so on and so forth. Okay. All right. So this is probably the most important message of the school. Enjoy it. Okay, fine. We are going to try to sort of sweat you through. Please enjoy that journey. Okay, fine. So let me stop at this point with this welcome message, and I'll take some questions at this point, and then on we'll start up with the actual technical content. Any questions, issues so far? You have had an idea about how the school is has been designed. Okay, you're all set to go. Fine. All right. So let me start this up by, I promised you an assignment. Let's begin this school. Okay, I promised you an assignment. First one, simple one. Write a C program to sort n natural numbers. These assignments are better done on machines, but if you wish, you can do it first on your paper, whichever way. Is the problem clear? Problem clear? And okay, we assume that you know C. Is that okay? Or is our assumption incorrect? Anybody with who feels that array they don't know C? Okay, good. If this is about programming languages, you should write programs. So here is the one. We begin by writing programs. Write a C program to sort n natural numbers. Okay? Done. On the machine? You would want to do it on the machine? Okay. Right. I just had a quick look through whatever you guys are doing, and here is one idea. I think that I should be talking all the lectures in C rather than normal human English. That's because almost everyone wrote C programs by hand in their notepads. All right, fine. So C programs are supposed to be written on machines. Incidentally, I saw some of you using Turbo C, which is suggested not to. We would suggest you strongly use GCC. Okay. Now, what we want to really do is take this scenario and think about what we did when we were told to write a C program that sorts natural numbers. What did we do? Think about what went on in your mind, what you actually did. Introspect. Okay, fine. All right. So, for example, which sorting algorithm did you use? Okay, let me ask it like this. How many did not use bubble sort? One. How many did not use bubble sort? One. Only one? Come on. 2, 3, 4. Cool. 5. So, which sort algorithm did you use? Selection sort. Okay. You? Insertion sort. Huh? Then? And then array. Okay. So, how did you do that using a temporary variable and an array?
Using the temporary variable, I read all the numbers, and I took as it is an unnatural numbers, the array indexes will start from 0 to n minus 1.
Right.
So I read that variable and I placed it in its appropriate position in the array.
Okay. Fine. How about you? Similarly. Insertion sort. You don't have to stand up, you can just sit down and answer. All right. So, non-bubble sorts were selection sort and insertion sort essentially. Okay. But that is something that you must have thought about, which sort algorithm should I use, okay, or how should I sort. Maybe you did not think of it so explicitly. You just said, okay, I am supposed to sort numbers, chalo. But this is a time to take a step back and think about what you did. Okay. What did you do when you were told to write a C program which sorts n natural numbers? Fine. So, let us start. You guys just keep on telling me your ideas. What went through your mind? What questions, what answers, how did you make choices as you decided to write a C program? One example was choosing an algorithm. What else occurred in your minds? Yes. Sorry, one second. Yeah, please take a mic. Yeah.
So I thought we will be teaching, so huge data will not be there. So I thought that insertion sort will work or bubble sort will work.
Okay, so you went through bubble sort. Okay, but you thought about the size of data. Okay, anybody else? Just take a mic. Please take a microphone. Okay, in the meanwhile, while they set it up, yeah. That it is easy to implement bubble sort. Let me sort of get this thing here. Anything else? Bubble sort is easy, size of data. What else went on through your minds? Structure of program. And all right. So, fair enough. Now, this school is for you. What do I mean by an algorithm? What do I do when I write an algorithm? In your mind, you had some algorithm, say bubble sort, selection sort, insertion sort, or whatever. And in your mind, you thought of some operations about that algorithm. And those thoughts about whatever manipulations you need to do, you wanted to write them. All right. So, what do I do when I write the algorithm? What do I do when I write it in C as opposed to Python, C++, assembly, x86 machine language? I hope you know the difference between a machine language and assembly code. Fine? Okay, cool. I mean, what do I mean by an algorithm? That is one question. What do I mean by writing an algorithm, then writing it in C or Python or whatever, or in your favorite or the language that you hate the most, whatever it is. Lisp, for instance. How many of you like Lisp? Or I like Lisp, okay, which is of course the reason I am asking you. I am just flirting with all of you. But anyway, did this question strike you? How do I know if I have correctly written it? Did this question strike you? Yes or no? I mean, did this question strike you? Then why did you not say it before? Anyway, again I am being a little mischievous. How do I know that my algorithm is correct? How do I know that? I may have done all that other whatever of writing and so on and so forth, but see, my point here that I am making is, well, just giving an assignment, and when we say write a C program to sort whatever natural numbers and so on and so forth, that is pretty fantastic, all right. And the moment we are given an activity, it's our natural instinct to just go out and start doing it, and maybe it is worth stopping for a moment and trying to think about what have we done, what are we doing, all right. In fact, for the day, for today and the next day or two, it is these questions that we would want you to keep on thinking about. What do I really do when I write a program? What is it that I need to do? What do I mean by writing a program? In my mind, there is a program, there is an algorithm, concept part, and the writing part. When I create a real stuff out of it, from my mind out through my hands onto the machine, what really is happening? Okay. Fine. Here are just a few questions. Your real assignment is to write down all the questions that you have and share them tomorrow morning. Is the assignment clear? The real assignment is not about writing C program, that you have to write. Okay. In maybe different sort algorithm, apart from bubble sort, you also write in whatever insertion, selection, merge, quick, or whatever sort you want. Write in a few sort, use a few sort algorithms to write it. Write that C program. Okay. And keep on thinking about what is it that you are really doing. Introspect. Ask yourself some questions. Think of some questions. Try to answer them yourself. Fine. And your assignment tomorrow is to give us a list of those questions. That is the assignment. Fine. Is that fair? All right. Everybody understands clearly. Anybody with does not understand it? What is to be done? Point 1. You started writing program to sort natural numbers. You did that. All right. You wrote it in C. Then we asked you, what do you mean? I mean, what did you do when you actually wrote a program? Think about all the stuff that went through your mind, and so on and so forth. We have given you some possible questions that might have come to your mind. In fact, you said that some of them did come to your mind. So, what do I mean by an algorithm is one possible question. What do I mean by writing an algorithm in C, Python, C++, or whatever set of languages? How do I know that I have correctly written it? Okay. These are just some of the questions. There could be more. There could be different questions. All right. All I am saying is, throughout the day or today's day, you will spend writing code, sort algorithms, not just one way, but multiple sort algorithms. Okay. Fine. And while you do that, not only should you get your sorting algorithms running right, that of course is there, nobody wants wrong programs. Fine. Agreed, right? Wrong programs not wanted. If you agree with me, then I have many wrong programs that I have tried to write. You just buy them from me. That is, pay me money for wrong programs. If you are agreeable to that, I am happy. Fine. So, we need to get our programs right, and while we are doing that, again at the back of our mind, we are also going to think about what really are we doing. We want to be conscious, more conscious than before. Okay. Fine. So, please do these parts. This is the assignment, that write programs and think about what you do when you write programs. Is that okay? Fine. So, let me start off the review now. What do I really mean by an algorithm? Well, this was historically this was a question that was pretty important in the towards the end of the 19th century, and one of the greatest mathematicians of the 19th century, David Hilbert, came up with his list of problems, one of which was this. Okay. I mean, he of course did not talk in terms of models of what is meant by computation. The idea was simple. Let me give you an analogy. Let me sort of describe the idea intuitively. What did mathematicians of that generation or that time, what were they occupied with? So, see, in mathematics you have various kinds of branches, calculus, discrete mathematics, and many others. But whatever is the branch, one of the things that you try to do is take a statement and try to prove it. Okay. And if you are successful, that proof, I mean, it gives you a theorem. The point is, what Hilbert thought was, look, whatever I am doing, my idea about proving is quite, I mean, the way I go on proving is quite similar in almost all the cases. I have a statement, I apply some kind of a deduction system to come to the next statement, and so on and so forth. The process of proving is quite same with whatever be the specific branch of mathematics that is being talked about, the proof is the same, right? So, if we study this process of proving and try to understand it, there will be something very interesting that is happening. Suppose, for instance, you have a very complete understanding of this proof process. It means that this idea, proof process, can be just applied to a field and you will immediately get theorems, very mechanically. All right. So, his idea was like this, can we sort of study this thing mathematically? Okay. Now, in those days, the idea of an algorithm was very intuitive. I mean, you somewhere in your heart you knew what is an algorithm, but people never really clearly specified it. This is what I mean by an algorithm. An algorithm is this. That is not what was done. Okay. So, Hilbert gave out this problem of, okay, how do we sort of do this business of capturing the essence of this process? How can we do it? And of course, I mean, a number of people started attacking that, and this problem was solved somewhere in the 30s in different ways. One of them is, of course, Alan Turing and his Turing machines. There are other ways. The idea was what, in fact, let us look at Turing machines. Turing machines are known to everyone, right? Everybody has done that course, not an issue. Okay, cool. So, the key idea there was, well, an algorithm is something, today we say it as a step by step process, but what really we are thinking about is this, that whenever we describe something so clearly, the steps etc. are so clear that we do not need to leave anything to imagination. All the steps are crystal clear. That probably is something that is an algorithm, but this is a very intuitive idea. By intuitive I mean we as human beings, we understand it. All right. But if we want to sort of study it, the genius of Turing is in this idea, is in this thought that not only should human beings understand it, but if you want to talk about clarity, then a machine should be able to do it. A machine does not have intelligence, imagination, and all those things are absent. So, if a machine if we understand an idea and we can make a machine do it, that would mean that we understand that idea very well. All right, fine. It is in that sense that Turing machines are created, that they represent that clarity of understanding, and anything that will be executed by a machine will now be an algorithm. Okay. Now, the idea of an algorithm is independent of our own biases, our own imagination about what do we mean by clear. No, clear means machine can do it. All right. So, that was the key part, that insight about what really is an algorithm was answered by Turing by giving out his machines. It is in that sense that those machines are mathematical machines and not physical machines of the way we really normally understand it. Okay, so, you would have done finite state machines, push down automata, Turing machines and so on and so forth, and language is based on them, on this view of computation, C, C++, Java. Note that I am putting C and C++ in the same level. Normally they are thought of as different. C++ is object oriented. No, that is okay, it is object oriented, nobody denies that, but the underlying thinking there is very much Turing machine like. In contrast, another bunch of people, Alonzo Church, led by Alonzo Church, they came up with a different mathematical model called as the lambda calculus. Okay. How many of you have heard of the lambda calculus? 1, 2, 3, 4, 5. Okay, cool. So, that is the model of computation on which this languages like Lisp and Haskell or various ML, Camel or Camel and so on and so forth, they are based on these kinds of this view of computation. Okay. We will give a quick view of that, maybe because not everyone really knows that. So, we will sort of brush up about the lambda calculus a little bit. Yet another view is mathematical function, partial recursive function. This is in some sense more traditionally mathematical. Okay. The point that I am trying to make is, after Hilbert gave out his problem, different people attacked it from different ways, and here are 3 of them. Turing was connected with the first 2, at least that is what I know definitely. I do not know about the third one, but he is possible, because Turing came up with his Turing machines and actually went to in England and went to the US where Alonzo Church was working, and both of them together, I mean he worked with Alonzo Church on the lambda calculus also. In fact, Turing is famous not only for Turing machines, but far more critical are 2 other ideas. One, something called as a universal machine, and 2, he was the one who proved that all of these models are equivalent. In other words, this is computation, you look at it from this model, Turing machine view, look at lambda calculus, you look at partial recursive functions, whichever way you choose, it describes the same thing. Okay. So, I mean the reason why Turing is called the father of computation is not only because it is Turing machines, but because of such deep insights, something called as a universal machine, and all of these things are equivalent in their ability to express algorithms. All right. So, at various points we will be able, I just wish to fire up those memories in your minds about whatever you have learned. At various points through the school we will be using these ideas. These form your conceptual base, okay, in one of the pictures that I showed earlier. So, when you write a program, you have a sort of a mental model of execution, a C model or a C++ model, in the sense when you write a program you say okay, and a variable is going here, the way she described, temporary variable, take array. She talked in terms of arrays, right? But she just talked it, but I am sure almost everyone of you thought about it in terms of an array or whatever. But there is, what it means is that in your mind you have some model which helps you to, okay, if I have written out my program, then by I sort of run it in my mind and that this is how it works, and so on and so forth. That's a mental model of execution, but you also need a concrete model of execution, your actual machine. That's where we'll sort of review your hardware and architecture, a review whatever you have done there. You of course need a language for expressing. There are some syntax rules, there are some, I mean, some way, somehow you understand the meaning of those constructs that you write, and there is something called as an expressive power. This is again intuitive right now. I mean, you express the program in C++ or C, and you make a comparison which one was better. I could do it much better in C++, Java, Shava, whatever it is. There is something called as an expressive power, the same algorithm, but some languages allow me, help me, support me in expressing it better than other languages. Okay. So if you want to really contrast expressing your sorting algorithm in assembly language and C++, then you will have some sense of this, expressive power of one is better than the other. But what do we mean by expressive power? We have no idea. We just have a feeling about it. Okay? But these are some things that possibly go on in your mind. Is my program correct? Whatever I did, is it correct? This is a point where why we do mathematics, the thinking style in mathematics is very critical. So, in order to just put up my point, anyone willing to do this for me? Simple question. Show that x plus y square, okay, it's correctly written, x square plus 2xy plus y square. We did that. Anyone? Please come ahead, come forward and do it on the board. Okay. Is that okay? Anyone will have a different answer? You just have to show that x plus y square is x square plus 2xy plus y square, where x and y are natural numbers. Anyone with a different answer?
By providing numbers for x, values for x and other value.
So, you say that by providing numbers, specific values for x and y. So, x is 2, y is 3, all right. So, you show it that 2 plus 3, 5 square on the left hand side is 25, and then you have 2 square 4, y square 3 9, and 2xy kitna hota hai? The sum is total to 25. So, that work for 2 and 3. Then for next pair of numbers, right? Next set of values, say 1 and 67,431, right? Using area of rectangle. Can you show the area of rectangle method? Area of rectangle method. Okay, fine. Can you show it, please? So, here is area of rectangle method. The pen is there. So, the area of the entire thing is, I mean, entire outer square is x plus y square, all right.
We have four of these triangles here. So their area is half into x into y, and since they are four, that becomes 2xy.
By drawing, there are four triangles on the outer side, each having a area of half xy. Because it is in, there are four of them, you have 4 into half xy is 2xy, all right.
And then this is a square. The side of this square will be root of x square plus y square by Pythagoras theorem.
By Pythagoras theorem, the side of the square will be square root of x square plus y square, all right.
Area of this square becomes x square plus y square.
So, the area of the square is x square plus y square, which is what we see set out to prove. All right, thank you. But was that the thing that you wanted to say? Same thing. All right, cool. So, fine. We have two different proofs. Anyone else? Yeah. X is equal to? So? X is equal to y, then we can prove. Okay.
Bracket x is equal to y, then y becomes x into x square, 4x square.
Okay. On this, the other side also. Okay. So, what she is saying is that we sort of special case it out. Let y be the same as x. Then on the left hand side is x plus x 2x square, that is 4x square. And on the right hand side also you have x plus x into x plus x and so on and so forth, which again gives you the same thing. All right, so we have had four ways. Two of them there are on the board, and the other two by giving explicit values, and by the x equal to y case. We have four ways of doing this. The two ways on the board that you have, which of them is better? Let me label them. So, this is method 1 and this is method 2. Which of them is better? How many say that method 1 is better? Raise your hands. Okay. How many say method 2 is better? Raise your hands. 1, 2, 3. How many are not able to decide which one of them is better? Raise your hands. 1, 2, 3, 4, 5. Okay, fine. So, if that is the case, let us hear out. So, since the people who were not able to decide, they are less in number, let me start by them. So, why are you, can you give me reasons why you are not able to decide between these two? Who would take? So, the amount of time that you are spending is the same. No. I mean, there is no machine here. This is thinking, right? I did not really think in terms of machines. I mean, I just said a problem diya hua hai. Okay. No, to prove it, the amount of time spending is, that's not, you don't, I mean, you can't judge what is the time taken here and the time taken here, therefore you cannot decide. Am I getting you right? Somewhat. Okay. I am just interested in the spirit. Yes. Who were the others? There were a few of you here. Yes.
So in both the approaches, there are no specific assumptions that we have made. So I can't decide which of them is a more generalized form.
So, no specific assumptions are here between the two. So, it is not possible to really know which one of them is more general. Okay. You had also put up, okay, fine, yeah.
X
but you know this case perfectly. So, because you have you are not very sure about this fellow, you are not being able to make a judgment. Is that the case? Fair enough. 1, 2, 3. There was some few other people who had raised hands who could not decide between the two. Yeah. Okay, so similar to him, that you do not know the second method, so you really cannot make a judgment. Anyone else remaining from the people? Yeah.
Actually, it depends on what the person like.
Depends on.
Depends upon how we are viewing the problem. Someone like more graphical structure. Someone might like mathematical structure.
Okay, so someone likes more mathematical structure, then he or she would rather like this one over this one. If someone likes more graphical way of doing things, then he or she would like this one more. So it's more of an individual taste, apples or oranges kind of a scenario. Okay, all right. So let's take up people who say that this one is better. So before that, anyone remaining from this not being able to decide crowd? Okay, so let's go on to this part. People who say that this is better, I mean, your reasons? Apart from the one that he said this is graphical. Yeah.
Personally, to me, this is more intuitive than the first method because I'll try to provide some context. Now that I know algebra, I can understand the first method very well. Back in 7th grade, when I was starting this first, I had no idea how this came because I didn't know much about how you multiply variables and stuff.
Okay.
Now I can understand both similarly, but 2 is more intuitive and it will help to understand.
This is more intuitive, which is why you prefer that. Okay, this is more intuitive. Any other possible? Okay, how about this one? Why is this better? Easy to compute. Okay, easy to compute. Yes. Huh. The intermediate steps are much more easier in the first one. Here you need these. Okay. All right. So thanks so much for pointing that out. I mean, here there are some assumptions which are, sort of obvious. For instance, you know the area of a triangle, how to compute that. Okay, you know that this is root x square plus y square and so on and so forth, that is known. These are some assumptions there, all right, in this particular way. In contrast, what are the assumptions here? I agree with the first time when you encounter this, but now that you know algebra, what are the assumptions here? No assumptions? xy equals yx, that is called as commutativity. Anything else? Huh? What? X plus y brackets. This is actually x, I mean I am expanding it, x into x plus y into x plus y. From here you go here and from here you come here. This is called as distributivity. Now, why do you, so I hope you get this idea that there is distributivity, there is commutativity and so on and so forth that is going on here. There are assumptions. Natural number multiplications is commutative. It distributes. There are assumptions like this, right? There are assumptions here. Can you now compare assumptions and say anything? Which assumptions are better? This, assuming this, which assumptions are better? First. How many say second are better? They are not. These ones are properties of the operators, multiplication, addition, these are operations that are independent of the actual values. In other words, whatever be the value, the property remains the same, it is invariant. Okay? You are reasoning out, these steps are based on properties that do not change, whatever be the values. That is why this deduction process is, I mean, this calculation, you do not really worry, even it will be true for any x and any y, not specific x or specific y. The mathematical thinking style here is, if you want to show something, try to use reasoning that is based on invariance, something that does not change, use that to perform your manipulations. Okay, fine. To be honest, over here there are those assumptions are also there, but they are very implicit. I will have to separately prove triangle area, one can do that, this can be shown, but the point is all of this is now dependent on this intuition and just expressing that intuition, all right, whereas this is pure algebra. What do I mean by pure algebra? Reasoning is based on using properties, behavior that does not change with values, in fact it is independent of them, which is why you are all confident that whatever be x and y, this will be true. Fine. Am I making sense here? Now look at this question. How do you know that your sort will work for any input? That is what we are concerned with, right? We would not want to have a sort algorithm which will work for some specific inputs. When you test, you are going to give few sample inputs and verify, but whatever you do, that verification will be only for the set of values that you actually used for checking. That will not give you a confidence that it will be there for all values. So, just like we had some kind of a way of figuring out that this business is true for in the mathematics way, we use that mathematical thinking style to actually prove algorithms. Okay? How do compilers work for any input programs? I hope you can see the connections now. There is a certain issue that is there in languages, and that is something that we have also faced before. How is it that we achieve that confidence that whatever we are saying, x plus y square is whatever, how are we so sure that it will work for whatever input it is, whatever x and y they are? That thinking style has to also be used in the case of computing. Not only at the level of an algorithm, but even at the level of the language. Compilers, they will have to deal with this. They have to work for any input program, right? Fine. Okay. Let me stop over here.